Hello YouTube, and welcome back to part 2 of the Basel Problem series. So I hope you got to have a little bit of pi for pi day, right? But now let's jump right back into the Basel Problem. So I said, so I highly suggest if you have not seen the first part, please do, because this proof may seem a little bit more hard to follow if you haven't had sort of the previous more conceptual understanding. This proof definitely builds off of that. So without further ado, let's jump right back into it. So we talked about last time the sine function. We talked about how we could break down the sine function into its linear factors. And so simply if we just divide off of pi x, this is pi, which is the infinite product of 1 minus x squared over n squared. And so this is what we had. Remember, we had it was simply pi x times 1 minus x squared times 1 minus x squared over 2 squared, etc. So that's what this is. And we can rewrite this, though, in a way that's going to be a little bit more helpful, and you'll see why. We can, instead of saying 1 minus x squared over n squared, we can get a common denominator and say n squared minus x squared over n squared. Okay. And again, this will be, we discovered this heuristically in the last video, and this will be proven in the Weierstrass factorization theorem. But so the first step is we've gotten this. Okay, well, if we take the natural log of both sides, it's kind of written right on the edge here. If we take the natural log of this, the natural log of that, right? Well, what are we going to end up with? We're going to have the natural log of the sine pi x, then minus the quantity of the natural log of pi plus the natural log x. And now you might be wondering, well, how are we going to deal with this infinite product of n squareds minus x squareds over n squareds? Well, it's really going to be the same idea, except our infinite product becomes an infinite sum, and then of the natural log of the quantity of n squared minus x squared minus natural log of n squared. And this should make sense because if you recall, adding two natural logs is like if I had, that's why I can do, like, for example, this, the natural log of the quantity of pi x is the same as the natural log of pi plus the natural log of x, right? This multiplication becomes addition with logarithms, and vice versa. Division becomes subtraction. So it should make sense if we're taking a natural log, a bunch of infinite sums for natural logs is really just infinite products. So kind of interesting little thing there. Okay, well, next, if we can differentiate both sides of this equation with respect to x, if we differentiate both sides with respect to x, what do we get? Well, chain, right, so pi times the derivative of sine is cosine, and then just over sine pi x. And then the derivative of a constant is 0, and then so it's simply minus r1 over x. That's going to give us this still then this infinite sum. Now this will become negative 2x over n squared minus x squared. Okay. Now, we need to get rid of that. Let's just, if you multiply by negative 1 over 2x to get rid of this 2x here, we do that to this whole thing. What does this end up giving us? Well, negative pi cosine of pi x over 2x sine of pi x plus 1 over 2x squared. And on the right, we are simply going to be left with this infinite sum from n equals 1 to n equals infinity of 1 over n squared minus x squared. Okay. Now, what can we do at this point? Well, if we make a clever substitution, then things start getting interesting. If we let x equal negative I t, and then therefore x squared be negative t squared, because it's negative I t times negative I t, the negatives cancel, we're left with I squared t squared, so negative 1 t squared. What if we plug that in? Well, this is going to give us negative pi cosine of pi, not x, it's going to be pi, negative pi I t over negative, so 2x is going to become negative 2 I t sine of negative pi I t. And then we know just simply these, so this minus is going to go away. And then minus 1 over 2 t squared. That's going to give us the infinite sum from n equals 1 to n equals infinity of 1 over n squared plus t squared, because minus a negative gives us positive. And there's a huge important thing we should note. If when t equals 0, we get the Basel problem. We get the Basel problem because if you recall, the Basel problem is the infinite sum from n equals 1 to infinity of 1 over n squared, right? So if this n is 0, or this t is 0, we're left with 1 over n squared. So it's a very, very key thing. Keep this in mind. Okay. Well, now we need to simplify this expression here. And so I think I'm going to I'll erase this stuff up here so we can have more room. So very dusty. Okay. And so to do that, why don't we take a look at cosine of z over sine of z. Because you can kind of see from right here, we know we have some constant, or some coefficient, and then cosine over sine. General idea. Okay. Well, how can we express sine and cosine? Knowing that we have these I. We have I and we have t. Well, this is a very exciting moment because right now it is like, this new melody, or this violin sort of coming out of nowhere and just enlivening the whole symphony. Because we shall now turn to to Euler's famous equation. And I did a whole video on this, just deriving this. definitely watch that if you haven't, because it's really, really cool. But yes, we're going to use Euler's identity, and this is just one example of how ubiquitous this boy is. I mean, Euler's identity is just popping up everywhere, really is, and this is this beautiful, though more rigorous proof than laughing, is going to utilize this identity, this jewel, in the words of Richard Feynman. And then it's also going to be important to note that IZ is going to be cosine of z minus I sine z, and you can derive this the same way as this using Taylor series for sine and cosine. But now we shall continue. So if we want cosine, well, if we add e to the IZ and e to the negative IZ, it's going to give us 2 cosine of z, and then plus I sine z plus a negative sine I sine z is just going to cancel. But we don't want 2 cosine of z, we want cosine of z, so that's what we multiply by that 1/2. Now for sine, similar idea. We're going to want to, except we're not going to add, we're going to subtract. We're going to take e to the IZ minus e to the negative IZ. And we can see that we have, because with the minus we get rid of the cosine, and then we have I sine z minus a minus, so plus I sine z, so 2I sine z. But we don't want 2I sine z, so we need to divide by 2I in order to get rid of the I and get rid of the 2, so we just have to that side. Okay, so now this will become I, and then get rid of the 1/2, bring up the I. We know that if we factor an e to the negative IC out, this is going to leave us with e to the 2IZ plus 1. We can do the same on the denominator. Factor out e to the negative I z. This is z. Factor out e to the negative IZ. And we're going to be left with a similar thing. E to the 2IZ. But we're just going to be minusing 1. And then we have a common, we just pull out a common factor, e to the negative IZ. So that will cancel and will leave us with this. Okay, now remember, if you look here, this z, right, this z is really negative pi it. So I'll erase Euler. So if we plug in negative pi it, we're going to get I times e to the 2 pi, so it's going to be 2I times z, and we know z is negative pi it. So, well, I squared is negative 1, but times negative is positive. So it's simply 2 pi t. And so this is what the new exponent will be for these guys. 2 pi t plus 1 over e to the 2 pi t minus 1. Okay, and we can erase this guy. Okay, and then, so now we put it back in terms of z. So we can put this guy back in terms of this. So we're going to have pi times 2it, and then this is going to be I times e to the 2 pi t plus 1 over e to the 2 pi t minus 1. Okay, So, and then we'll just we'll leave this guy, this minus 1 over 2t squared. We'll leave that guy out for just a sec to simplify this first. So, this is going to become pi over 2t times, now how can we simplify this? Well, if we have a 1 and then we add 2 over e to the 2 pi t minus 1, then if we were to work backwards, get a common denominator, e to the 2 pi t minus 1 plus 2 gives us plus 1, and the denominator is the same. So that's that. Okay. And so then this would just become, if we multiply it out, pi over 2 pi, or pi over 2t plus, and then that 2 is going to go away to just give us pi over t times e to the 2 pi t minus 1. Okay. And then now we can go ahead and add back in that minus 1 over 2 t squared. So we're just simplifying this. Technically I should have been writing this minus 1 over 2t squared, but just for clutter's sake, we are now adding it back in. Okay. And then, yeah, so we can just get rid of this. Okay. So, now let's start simplifying this down. So we have a 2t squared. So, quick thing we can just do, multiply by t, and that would give us, pi t minus 1 over 2t squared. But we still have this plus pi over t times e to the 2 pi t minus 1. So how do we get a common denominator here? Well, this one we can just multiply by 2t. This guy we can multiply by e to the 2 pi t minus 1. Very small, e to the 2 pi t minus 1. And this quantity right there, so e to the 2 pi t minus 1 times pi t minus 1, well, this is going to give us FOIL, right? So e to the 2 pi t, e to the 2 pi t minus e to the 2 pi t minus pi t plus 1. Just like writing that out, just so it's clear to see. So this is going to give us then pi t e to the 2 pi t minus e to the 2 pi t minus pi t plus 1. And then don't forget about this plus 2 pi t. Over 2t squared times e to the 2 pi t minus 1. Okay. So now we know that this is going to just become pi t e to the 2 pi t. Actually, I'll just simplify here. Now I'll just write it out one more time. Very nice and clear for myself. Pi t e to the 2 pi t minus e to the 2 pi t plus pi t, because minus 1 plus 1 gives me plus 1, and then plus 1 over denominator of 2t squared e to the 2 pi t rather, minus 2t squared. Okay. And you remember that we said that when we plug in 0, because this is really equal to like the infinite sum of n equals 1 to infinity of 1 over n squared plus t squared. So we said that if we plug in t equals 0, that will give us our Basel problem, 1 over n squared. So let's see if we can just plug in 0 here. Well, okay, 0, that goes away. Anything to the 0th is 1. So this would become a minus 1. And actually, I'll start writing this out just so it's clear to see. So if we plug in 0, plug in t equals 0, we're going to get 0 minus 1 plus 0 plus 1 over 0 plus 0. Well, negative 1 plus 1 is 0, and so we get 0 over 0. Indeterminate form. Does not exist, right? Well, poop, okay, shoot, so how can we do this, right? Well, there's an important rule. And this is going to be, we're entering the home run for the final stretches for the proof. So if we look at L'Hopital rule, we know that if we're plugging in, we're trying to take the limit of some value, and it's the form of f of x over g of x, right? So we have, it's a rational function, really two functions. If this gives us indeterminate form, i.e. 0 over 0 or plus or minus infinity over infinity, then we can conclude that the limit of that is going to be equal to the limit as x approaches a of f prime of x over g prime of x. In other words, if we get an indeterminate form like we did, we can just take the derivative of the numerator, divide that by the derivative of the denominator, and plug in our limit, or plug in our x, or our function value, and we'll have our limit, right? Okay, seems relatively easy enough. So then why don't we, so let's start taking some derivatives. I'm going to rewrite this function so it's easier for us. So pi t e to the 2 pi t minus e to the 2 pi t plus pi t plus 1 over the quantity of 2t squared e to the 2 pi t minus 2t squared. There we go. Pi t e to the 2 pi t minus e to the 2 pi t plus pi t plus 1 over the quantity of 2t squared e to the 2 pi t minus 2t squared. Okay, and I'll just go ahead and erase the bottom of this so we have full room for the rest of the proof. Wax on, wax off. Okay, so if we take the derivative of this guy with respect to t, right, following that the L'Hopital's rule, so this is going to be product rule, so we can just take the derivative with respect to this t first, so pi e to the 2 pi t, but now plus, well, okay, 2 pi squared, leave the t there this time, and then e to the 2 pi t. Oops. That t is in the numerator. So pi e to the 2 pi t plus 2 pi squared e to the 2 pi minus, well, what is this, just 2 pi e to 2 pi t plus pi, and then the 1 is a constant, just goes to 0. Okay, and then divided by, well, so this is going to give us 4t e to the 2 pi t. Now we leave the t squared alone, and we're going to bring the 2 pi down, so we're going to get 4 pi t squared e to the 2 pi t. And then this guy by himself, 4t. Okay. Well, if we plug in 0, and the 0th is 1, so we're going to get pi. So I'm just going to write here. We get pi plus 0 minus 2 pi plus pi over the denominator of 0 plus 0 plus 0 plus 0. Well, pi plus pi is 2 pi minus 2 pi. It's too many pi's. Over 0, 0 over 0 again. So we need to do this again. Still indeterminate, so we must do it again. So 2 pi squared e to the 2 pi t plus 2 pi squared e to the 2 pi t plus 4 pi cubed t e to the 2 pi t minus 4 pi squared e to the 2 pi t plus pi goes to 0. And then look at the denominator. Well, it becomes 4 e to the 2 pi t plus 8 pi with the t alone e to the 2 pi t and then plus this is going to be 8 pi squared this time, because bringing the pi down, leave the t squared alone, minus 4. Oof, okay. Well, let's gather some stuff. So we have 2 pi squared, times e to the 2 pi t minus a 4 pi squared e to the 2 pi t. So right away we can get rid of those guys. And so in the numerator we have 4 pi cubed e to the 2 pi t. And for the denominator, well, we simply are going to have 4, and then I believe, and then there should be one, I think there's one more term here I missed. 4 e to the 2 pi t, okay, plus 8 pi e to the 2 pi t, plus, so then get rid of this 8 pi squared, which should be 8 pi, okay. Too many pi's and e's and p's. Derivative with respect to t is going to give us 8 pi t. 2 pi t, there we go. Plus, okay, now for the second product rule, we're going to ignore t, take the respect to e. So that's going to give us our 8 pi squared. 8 pi squared t squared e to the 2 pi t minus our 4. And there we go. Okay. So, and then we have right here, there's our 4 e to the 2 pi t. 2. And then plus 8 pi t plus 8 pi t. This is going to give us plus 16 pi t e to the 2 pi t. And then this just plus 8 pi squared squared e to the 2 pi t minus 4. So, well, we know, okay, we can get rid of, if we factor out, so we can factor some things out, which is going to be important. If we factor out a 4 e to the 2 pi t, the numerator, that's going to leave us with simply our pi cubed. If we factor out again a 4 times e to the 2 pi t on the denominator, what's that going to leave us? Well, this becomes 1. This becomes 4 pi t. And this becomes 2 pi squared t squared. So that would give us 8 pi squared t squared e to the 2 pi t. And then minus that, minus e to the negative, minus, e to the negative 2 pi t. Because it's really, because if we were to multiply this, we get minus 4 e to the 2 pi t over e to the 2 pi t. The e to the 2 pi t's cancel, being left with a minus 4, which is exactly what we want. Okay, well, if we plug in a 0, we get, 0 is 1, so we get 4 t cubed over, well, actually, these guys cancel, right? So you get a pi cubed over 0, 0, 0, so that would not work. Oh, and actually there should be there should be a constant t. Yes, there's a t here, my bad. There's a t there. So we're actually left with right. T, E, and there, then you have 0 over 0. Again, indeterminate. So, we shall thrice differentiate to use the Caltech rule. Third time, and final, I promise. So I'll take it over on the top, and you're simply left with pi cubed. Denominator, 1 goes away, 4 pi. This would just become plus 4 pi squared t, and then this is going to be 2 pi e to the negative 2 pi. Just. Okay. Now, if we evaluate this at 0, right? So at t equals 0. This is going to give us pi cubed over, can you see it? 4 pi. That goes to 0. That gives us 2 pi. And voila. Pi squared over 6. And if you remember, because this was at t equals 0, that's the infinite sum n equals infinity, for n equals 1 to n equals infinity, of 1 over n squared. Woof! Well, that was by far a longer proof, and well, the mathematicians definitely have it right when they say it's a rigorous proof, perhaps vigorous too. So another very interesting, still I think a very interesting proof, because we are able to use the concept of Euler's identity, right? E to the I z equals cosine of z plus I sine of z. And so it's a really cool application of that identity, of that formula. So props to Euler for that. And now one other side note I'll make. You may have noticed my shirt. Hopefully you noticed that I had a shirt. But this is actually modeling part of the Riemann Zeta function. Riemann Zeta function looks like this, is zeta. So we actually found zeta of 2. And we know that, I'll write it here, we know we know that the Riemann Zeta function is the infinite sum, meter, kind of running out of room here, is the infinite sum n equals 1 to n equals infinity of 1 over n to the s. So obviously if we plug in 2 for s here, that gives us this. And there is actually a whole way to think about this problem and solve it simply by going straight to the Riemann Zeta function and then figuring out, oh, well, that's going to be when s is 2, and then evaluating it that way. And so I didn't take that route. I did it using Euler's identity and L'Hopital's rule, but it's still kind of cool. And this even goes back to the first video I did, thinking about this solution, pi squared over 6, not just in terms of, oh, well, the Basel problem, the infinite sum of the reciprocal of the squares, but putting it in the larger context of the Riemann Zeta function family, right? And if you if you consider yourself a math enthusiast, you may be familiar with the famous Riemann hypothesis. And that is what this shirt is actually modeling. It's kind of hard to see. I'll kind of lift it up so you can kind of see. But what it's modeling, you probably can't see it. Let me lift it up. It's modeling the input of 1/2 plus it. And the Riemann Zeta, the Riemann hypothesis, is that all non-trivial zeros of this function, and non-trivial, because essentially we would consider a trivial zero, as in already proven, already known, to be negative even integers. But you might ask yourself, but if I plug in a negative even integer, how is that going to converge to 0? I'd have 1 plus 2 squared plus 4 squared. How can that be 0? That's the reason. The reason behind that is it goes into the realm of complex analysis, and essentially for the fact that this function is only defined for s being greater than or equal to 1, right? Not going to the negative half, or I guess even when s is 0, it'd be fine to be 1. But so it's a whole really interesting field in pure mathematics about complex analysis and complex modeling, and that the Riemann Zeta function is at the heart of that problem. But so the idea with this shirt, I think it's really cool, is if we plug in the input 1/2 plus it, and what the Riemann hypothesis was that all non-trivial zeros will occur when the input, when s is equal to, I'll just write it here, when s is equal to 1/2 plus it. That will give us our non-trivial zeros, our non-trivial zeros. And this is what that looks like. And essentially, what you might be saying, well, why is this important? Well, and I know I'm kind of venturing off with this whole other topic, which really deserves to be explored in its own video, but essentially, there are so many other proofs in mathematics that rely on this definition. They rely on the Riemann hypothesis being true, and it's also critical in terms of encoding the pattern of the primes. Really, some really interesting, kind of crazy mathematics going on, but yeah, it is yet to be solved. It has to be proven, and so if you do solve this, then you actually you will win $1 million prize, I believe, from the Clayton Institute of Mathematics. I think is what it is. But not only that, you'd be solving hundreds of other, you'd be proving hundreds of other hypotheses, and I mean the fame alone would be outstanding. You'd be remembered in the history of mathematics, just like Euler, right? But that is for another day. Today, I still think it's interesting to at least kind of end considering the Riemann Zeta function, because that's kind of that's an application of this. It's kind of nice because it's taking this from sort of this more just pure abstract problem and moving it in a direction that really has a lot of profound implications. And I mean, this proof, it definitely is, yeah, it's a lot more time consuming than the previous one, maybe a little bit harder to understand, especially, I made a couple mistakes here I had to fix, but in the, just because there's so many pi's and e's and t's, it's just a little, it's more tedious, but I still think it's really cool using being able to apply what we discussed in terms of Euler's identity. So it was pretty fun. So, well, I hope you have a fabulous rest of your Pi Day, right? Have a math-tastic day, and hope to see you soon.